Okay, my friends, Mudfossil University, once again, home of the shocker du jour. I had done a big, long thing, and I was documenting it as I was trying to investigate how this Crookes Radiometer works. And that was a while back. And I just recorded it, and I came more or less to a sort of a standstill. Now I realize exactly how it does work. And at the end of this video, you will see exactly how it does work. And this has been a source of controversy for 150 years. This is back in 1879. They had this, and nobody could figure out how it worked. And even now to today, they're talking about incorrect theories, pressure of the light, Then they got partially correct theories. Then they got currently accepted theories, and it goes on and on and on. Now I'm going to show you exactly my process of understanding how this thing works. This is what research is all about, and this is how I do it. I record little bits and snips. That's why a lot of times everything seems to be out of order, and it probably is. But that's how research is done. You have to look at it, and then you think about it, and you add a little this. Oh, wait a minute, I forgot about that, and back and forth. And now I fully understand how this thing works. And this 150 years has been not understood. You see if you think I'm right or wrong, and it'll be at the end of this video. Okay, my outstanding friends, this is going to be a blast. I love doing this kind of stuff. This is a Crookes Radiometer. Now, I spoke about this a while back, and I did not have one to show at that point in time. Now I do. And I've been looking into it, and I've been looking into magnetism and all these little forces that they can't understand. They still don't understand the Crookes Radiometer. The current thinking is it's thermal transpiration. What that means is you got a black side and a white side. They think it has to do with how much energy it absorbs and therefore pushes back out. So it's absorbing and pushing, that type of thing. That is not the case. And I think I can prove that is not the case. We're going to do a whole series of tests on this Crookes right here that I have. And then we're going to look into magnetism, because I thought I understood magnetism. I did not understand magnetism, and I still don't. So I'm getting there. You know, I mean, this is not something you can do just like that. I didn't realize. I thought magnetism. You got a positive, you got a negative, and you know, inside of what they call polar molecules that have a bunch of different centers of positive and negativity in their dipole moments, they call it. So it's a molecule like this, or you know, pretty much a molecule like this, and there's a whole batch of different spots in there that are positive and negative. I understood that, but I pretty much thought a bar magnet is a bar magnet. You got a positive and a negative. Well, a round magnet is totally different than a square magnet, which is totally different than a bar magnet. There's all kinds of different configurations, even like this curved magnet, which they used in direct current motors, is different. And they can form these magnets in any kind of different way they want. So this gives me a whole new perspective on magnetism. Seriously, it's just not what I thought. Well, it is and it isn't. But I can see there's a lot more that I didn't understand, let me put it that way. However, it does fit exactly into my dipole electron flood theory. Now, we're going to be playing around with these little magnets here, and you see, they push each other apart, or they pull each other together. It depends on the way you have them configured. Anyway, we're going to get into this because it's very, very interesting. And it could lead to some discoveries of, you know, energy sources and so forth. I'm seeing people are experimenting with different types of alternative types of energy, because these are forces. That's a force. anytime you have a force, if you can figure out how to manipulate it, you can make it do something. That's a force. Now, if I can figure out how to manipulate these forces, I can make them work against themselves, and I think I already have. And all it requires is a venturi and a light source, a laser, really. And that'll actually divide the light apart and separate the white, which is the energy, from the black, which is the mass. We want the energy. Let's get into it a little bit. Now, this is an example. This is Rogrand, and he's over in Italy, and he's doing experiments with light. Now, he also did one the other day with light concentrated through a little tiny droplet of water, and I think he might have been actually exploding the water. Now, these are very brilliant. You know, he's sending light through here, and it's radiating back towards his camera, and it's pretty brilliant. And he's got, you know, I really don't understand the setup all that well, but the one that really turned me on was the one where he was going through the water, because he would focus in there and it would hit the water just the right way, and pow, it would just be absolutely just gigantic. The whole thing would just be white. Now, water is a very small molecule, a lot of hydrogen in water. Could he have been hitting it with a strong enough pulse? Because he went through 3 different phases of magnification mirrors, and then hit it, and it was just astounding, the amount of energy. Now, could he have been dislodging extra hydrogen, breaking the hydrogen up? I don't know. He had a little like hypodermic needle, and he was focusing in on it, and as he was squirting it in, he was hitting it with the pulse, and he was sort of wobbling it around, and as he did it, all of a sudden it would change colors, and then all of a sudden, pow! When he hit it just the right way, it was absolutely stunning. All right, I don't have the footage of the actual experiment, but what it was, as he was shining that light and he was holding a little blob of water, just to come from a hypodermic needle, and he was moving it through the light beam, and every now and then he would get it just right, and it would just go, and I mean more than that, it's just stunningly brilliant. Now, you see the edges of this? This almost looks like atomic vapor. And I'm going to show you where I see another place that has a similar look to it. Now, is this actually just light, or is this some kind of a particle coming off of this surface, which would be an electron? Which, when you have this extremely bright light, that's energy, and that's electrons. Now, let's go to the next shot here. These are ones he sent me, just pictures. And Rogrand's doing a great job over there. Now, this, and again, you know, we did a Zoom the other day, and it's kind of hard to fully understand what he's doing, but it's just another spot where he took a picture of it colliding. Now, what's exactly happening? Is this inside the water bubble and just sort of trying to figure its way around inside? Because there's going to be like surface tension around that bubble, which is nothing more than electrons glued together. Now this, I don't know. These are the kind of things, I don't know what he's got going on here. But blue I usually assign to an extremely interactive subatomic interaction. Now this, as far as I can figure, it's coming down this way, and he's focusing this way through a water film or something. And it's actually bubbling out the water down here because of the impact of the light. It's all I can take from this. And this is just a guess. And it's hitting it, and it's brilliant white, down around here where the concussion zone is, right at that little blip there. And then you're seeing this coming out. Look at the different colors. Isn't that something? Look at it. I'm just looking, just like you. I don't know. I don't know what this is. But this is what I'm seeing, and Rogran could probably help me out looking at it if I get him on another Zoom. But I can see, it appears to me, because I know he's focusing. I know he's focusing. And I assume that this is the focal point, exactly perfect on a spot of water or whatever. But isn't that something? And so what do you think you're seeing? I think I'm seeing, well, I know I'm seeing different colors. Well, what does that mean? Why would you see different colors? Why isn't it just white? Well, this is coming through like a lens, it appears to me now that I'm thinking about it. This is creating a lens effect where, in like a prism. I think that's what it is. But isn't that something? This is spectacular stuff. And he's just doing it on his own. Nobody's funding him. He's just trying to figure this out. Look. Look at the light coming off of that thing. This is like a... It's hard to understand any of this stuff. Now, apparently there's a university over there. He thinks they might be interested in looking into this, which would be fabulous, because nobody here in the United States will even respond to any of my emails, and I've tried many times. It's just I'm too invasive to their territory, I guess. But that's interesting stuff. And what that is, I don't know. What would create that? And these little blobs, these are things that need to be looked into. And how is he taking these pictures? What is the resolution? All that stuff. And I agree. And everybody say, oh, you got to tell this and figure out that. Well, yes, I agree with that. But all the stuff I have shown was from a Samsung Galaxy S3 CMOS phone. And they very clear. And CERN recently upgraded to use CMOS because it is so spectacularly clear. And every CMOS pixel has its own amplifier. So, and they're made to pick up radiation, not to interfere with the radiation, just to pick it up. And that's what was wrong with CERN. They always had something, they were forcing light into it, or they had some device in it that was picking up the magnetism. They say anytime you look at it, it changed the outcome. No, they were forcing more energy in or taking energy out to sample it. When they did that, yes, it changes the outcome. But if you stand out here and you let the stuff hit you in your camera, well, it's just going to go somewhere else anyway, so you're not interfering with anything. And that is what CMOS does. This is just so bizarre. Again, I think I told you, I thought I understood magnetism. I did not, and I still don't. If you take these all have the same polarity, and they're basically the same magnets, just have different colors. So if I take these two, and I try to push them together, can you see this? I'm going to try to push these together. Watch what happens. It won't. It pushes away, pushes away. Now, watch this. They try to find another magnet that wants to attract them. Well, watch this. These are two same magnets. They should push each other apart. But I took one little tiny ball magnet and I put it in between, and watch what happens. Now they attract each other. You can't do that with this. It's not going to do it. No. That's magnetism, very strange right now to me. I'm having a hard time understanding it. But it has no effect on the Crookes radiometer. All right, I tried all I could think of to affect that. So it doesn't affect the Crookes radiometer. So magnetism plays no part in this. However, the field either pushing or pulling is causing these vanes to move one way or the other. And believe it or not, we can move it in both directions depending upon how we hit it with the light. And I'll show you that in a second. Now, I think I understand why this effect works the way it does. Now, they're talking about transpiration where the white would not absorb any energy. All right, so it would be colder on this side and it would be hotter on this side. Hotter means it would push. So the black would push away this way. All right, so if the light hits the black will heat up, push out this way, and the white will go that way. Remember that. Let me go get the flashlight. All right, let's test the theories. So if we have the black side and we take a very strong, bright, focused light and we hit that black side, what should it do? Let's see. There it goes. It's taking right off. Boom, 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 boom. Very quickly, it takes off as the white hits it. So that could be transpiration. The white is being absorbed by the black is kicking out, or is it just that the white is pushing the black? All right, so now we saw the white pushes the black, the light pushes the black very rapidly. Now we're going to be working with the white side. All right, so let's let it settle down. And I'm going to face right into that white. Now what would you expect to happen as I turn this into the white and just hit the white? All right, would you expect it to go that way? Or do anything at all? Watch what it does. It pulls towards the light. Why would it do that? Why would it pull towards the light? Explain that one to me. All right, the black got pushed away. It's going in the same direction. But this time we're hitting the white and pulling it towards us. It goes in the same direction, which either way we go. All right, so remember, here we are with the black. Zoom, there it goes, taking it right off. Boom, 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 boom. Now we're going to go to the white. And the white keeps attracting too. Either side, doesn't matter. So what is going on? Okay, now watch this. We used light before, and you saw what happened. And I can show you the different lasers. The blue will make it work, and the green will not really make it work, and the green and the red absolutely has no effect on anything. So there is a different energy level to the blue that forces it to do something. Now, what he's going to show is what heat and cold does. Now he's going to take a cold. I'm going to just play it, and he'll show you. Here it goes. This is Ben from Applied Science. Here it goes.
The refrigerant on the glass envelope of the radiometer. And as you can see, it's actually spinning backwards relative to the way that it was spinning when we shined.
You see that? It's spinning backwards. Every time we shine light on here, whether I shined it on the white, it would spin that way. Whether I shined it on the black, it would spin that way. So we were spinning this way from the light, which is a source of heat. Now he's doing cold, and it's going backwards. It's coming this. Well, hold on a second. Let me be sure I'm right here. This gets confusing.
I'm the light bulb on it.
No, it's going the wrong way. Watch this. Here's mine, here's his. All right. Let's go back a second and watch what his does. All right, now this is with cold. So he's spraying cold. Basically, it almost looks identical. You see it? So he is pulling energy out. I'm putting energy in. And I don't care whether I hit that one there or I hit this one here, it's still going to turn this direction. He's making it go that direction, so he's going to make it go in the opposite direction. This kind of stuff can be confusing. Now, here goes. Watch what he does. He's
And as you can see, it's actually spinning backwards relative to...
Exactly. It's spinning that direction. Watch what we do. Here he is with his. I'm going to put right here. It comes back at me. It's coming back at me. If I hit it the black, it takes off like a rocket ship. If I hit the white, it pulls back at me. It never is going to go that direction. This one goes that direction all the time. When it's
the way that
cold.
it was spinning when we shined the light bulb on it. So clearly there is something else going on here. If it were just a photon effect, making the glass envelope cold would not cause it to spin backwards because we aren't...
See, exactly. Exactly. Now, so what is your take on this? Stop and give us some thought. All right, I tried playing with the lighter here. Now, I don't know if I can do anything with this. Now, he hit it with the cold, and it forced it to spin backwards. So I would think if we hit it with the heat, it would force it to spin the normal direction. So let's try it here. Yep, look at that. It's making it spin in the normal direction. So we're not necessarily working with light here. We're working with temperature. Light is a temperature on its own, even though you don't see it that way. So let's think about what we have to think about here.
Glass envelope cold would not cause it to spin backwards because we aren't pulling photons out that way. As you might have guessed, the effect is thermal, and it does require that there be some gas in the radiometer envelope. If there were no gas at all inside here, then the only thing that could touch the rotor and make it spin would be the photons shining on it. And we've determined that can't be right because the photons would be making it spin the other way.
Okay, let's think about all of these things, because first of all, when he says the photons make it spin the other way, I don't think anybody has ever taken into consideration the glass. Now, let me point out something to you here. He's shining light through here, and it's making it spin one direction, and then he's putting cold in here, it's making it spin the other direction. Well, light is absorbed. Well, something happens to light in glass, because here's my proposal to you. All right. Think about this. If you're out in the sunlight, and you're not behind glass whatsoever, you get a sunburn, and you get a bad one. With glass, if you're behind glass, you don't get a sunburn. All right. If you're just laying in on your floor behind a glass door, you don't get burnt. If the door was open and there was no glass, you get a sunburn. Now, so why? Well, the electron dipoles are coming through that glass. They're two pieces, and one of them has mass and one of them has no mass, but it has the energy. The energy part, I believe, is what is burning you. So the glass must absorb some of that energy and apparently let the black particles come through. Maybe it's absorbing the black particles too. I'm not sure. But we have to think about that, because the glass is never been thought about before. It's absorbing something. It's either absorbing the black or the white or both. So that's what we got to think about. Is there any interaction because of the glass? And I think there might be. You know, they had always wondered why the black would be pushed by the light. They would think the white would push faster. The black would push, but not like the white. So they would think the black would make it go this way and the white would make it go this way. Why does the white suck up to the light? That's the key. Who can explain that? Explain that to me. Watch this. Why does that vein pull towards the white? Why does it pull? What effect does that white have? Why is it sucking it up to the light? Now we know if we hit the black, it really takes off. But if we hit the white, it still comes towards us. Why is it pulling towards the light? All right, this is just stunningly cool. If you shoot the light at the white, you would expect it to push the white that way, not to pull the white towards the light. Why would it pull it towards it? And it does. Watch. Here it comes. You see? It's coming towards us, towards the light. It wants to be into the light. Now, if I pointed at the black takes off real fast. But the white comes at it too. If the black pushes, the white is attracted. How could that be? How could that be that the white is attracted to light? The only possibility is magnetically. It's magnetic attraction. It has to be. All right, my opinion of light is it has energy, no question whatsoever it has energy. It has some push to it, but I don't see it having any suck to it. All right, and that's what's happening. Watch. There's no question that's what's happening. You see it? And it'll start taking off pretty good. So the white is being sucked to the light. Now it also pushes against the black, but it sucks against the white. Like I said, the only possibility is there's a magnetic polarity there that's saying, I want to touch the white light. I want to touch the particles of light. Why would it want to come this way towards the light? What is drawing it towards the light? Let's think about that. And I think I have a possible solution to this. And it involves a glass. Okay, the only possibility I can think of is that the glass has absorbed the black matter, which will attract the white. The black always attracts the white. All right, white pushes away from other white, but it is desperate to get to the black. And that's why when we shine the white light in here, the only thing that's possible, as far as I'm concerned, is that there is a heavy amount of black here, stays here at the glass, and more electrons go through the glass and leave behind the black, and that electron density here wants to pull back to the black, because the black didn't go through. The black is waiting for this stuff to come back, and it does. All right, if you want to think of it as polarities, when you shine the light on the glass turns positive. It has to be absorbing more of the black particles than the white, and it's letting the white come through. But it just doesn't make sense, because you don't get burnt from behind the glass. And I always think the white particles, the glowy white ones, are the ones that burn you, and not the black ones. I need to think about this. Well, the more I think about it, it appears that because the white pushes the black very quickly, the white is coming through pretty strong. All right, because the black doesn't really push the black. I don't think the black really pushes itself that much. I don't know now that I'm thinking about it. It could be the black is coming through real strong, pushing the black. Let me think about it. Okay, what I'm doing here is little clips of confusion. This is confusing. We're dealing with the dark particles and the bright particles. And they have their own separate way of dealing with other particles. The black couldn't care less about being attached to another black. They'll just lay on top of each other, no problems. But they're solid, like balls, and they can't get bigger or smaller, and they have all the weight, basically. The white ones can get big and small. You see, small and big, and it depends on how much energy the field is getting concussed. It must be like a giant soap bubble, or a tiny, tiny soap bubble, but when it gets pushed, it fluffs up big. It still doesn't have any mass to speak of, because it has virtually no mass, but has all the energy. I don't know how to account for that, but it is what it is. Now, these two particles have all the energy and no mass, and they are extremely attracted to the black. That's the only reason they can get so close to each other. They would never get this close to each other, ever, 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 if they weren't next to their black partners. They would be way out here somewhere. All right, but they have the black part, and I can actually show that here, as a matter of fact. You see these? You see this? You see down there? They won't go together. All right, they bounce apart. Now watch this. I take even just the tiniest little particle, a little magnet, and I interrupt that magnetic field. Watch. You gotta get it on the side of the magnet. Now watch this. So they want to be attached, but they need a field. This is nothing more than a dipole in between these, and it makes it work. Without that, you're done. With that, you're good. Without it, you can't get near. So that's what's happening here. They want to be snuggled up tight, tight, tight. That's the tight, strong nuclear force. And it's all magnetic interactions. These are nothing more than bar magnets. And these are the tiniest particles the Fermilab or anybody's ever seen, which is because they're the tiniest particles that exist. That's a muon, and that's dark matter, and it's gravity. And that is what attracts the white particles, which have no mass. And I should show that in an atomic bomb blast. The blast goes off, and everything just burns up, because the white particles are on the outside. They go first, have no mass, but all the glow, and they burn everything up, and then the black stuff comes, and off goes the house. So this is not something that's hard to understand. The thing that is hard to understand is the glass here having an effect on this. Now we know that the gases inside here are very limited. There's not a lot of gas, so it doesn't have to plow through a lot of particles. So that's different. Anyway. Okay, I'm asking, why does the light shining on the Crookes radiometer pull the white back towards it? It'll always spin in this direction with light or with heat. With cold, it spins the other direction, so it's related to temperature. This is very obvious because I used a lighter and warmed it up, and it spun just like it would if I put the light on it. And when Ben sprayed it with some coolant, it went backwards. So cold makes it go backwards, heat makes it go forward. I believe what's happening is the glass itself becomes polar, and it absorbs to me, it must be the black particles, because then anything that has white particles on it, which is everything, will be attracted to it. So I believe the glass itself becomes actually the more black particles in the glass, and that could have something to do with silicon. I don't know. But there's, or maybe even it isn't even silicon. Maybe it's plastic. I don't know what it's coated, really, but I believe it's holding some of the black particles in the glass, shining through it, or with the heat, and letting the radiated ones, the white ones, go in. And in this case, the white ones will always be attracted to the dark. So if the dark is in here, stuck in here, in a little bit of an excess, anything inside will be attracted towards it, which will be the veins will be being pulled out towards the glass. That's the only thing I can come up with. That it's a excess or an added amount of electrons in the glass. Because when he sprayed the coolant on there, the glass got extremely cold. So let's just take a second to think. If the glass is extremely cold or the glass is hot, what is the effect? You know, I was just wondering myself, what if both sides of the vein were the same color? Because the black is going to have an attraction to the white. The white is going to be attracted to the black. The white is going to be pushed away from the white. All right, this is something we got to think about, because the black absorbs white. White pushes white away, but black has no effect. Black and black can go together, just have no problem. They can click right together. They don't have any effect on each other. It doesn't appear. They can come into a ball, no problem whatsoever. However, they will attract the white, so the white will always surround the black and just push it into the center. In the case of this, you got one side's black and one side's white, so one is going to be pushed and one's going to be pulled. But when we're using the light, they both go the same way. Very, very, very confusing. And when we're using the cold, they both go the same way. Well, it just goes one direction with the cold, and it just comes in one direction with the heat. It doesn't matter whether it's heat, whether it's light. Let's stop and think about this. I'm going to do a little drawing here. Okay, my friends, looks like we got this figured out. I'm almost sure. Now, here's the deal. This is inside the Crookes. Okay, so here's the Crookes Radiometer. And inside is those veins with the black and the white side. So I'm simulating those veins. Now, in addition, inside here is almost a complete vacuum. Very, very few sparse particles. You see how I'm showing here? Out here, outside this side, they're all over the place. But in here, just a few. That's why it can easily spin through that medium. Now, here's what's happening. We know that anything with heat or light will make it spin this direction. We know anything with cold, when he sprayed the cold on, it goes that direction. Now, the reason it would, well, why? Well, so what is the heat? Heat is nothing more than a lot of electrons coming in here that are charged up with extra electrons, really. And they bang into the glass, and the glass holds on to the dark particles because they are the heavy particles. It'll hold on to more of the dark particles than the other ones. They have no mass. They flow right through there. And they come out the other side here. You know, that's not right. Something's not right here. All right, this is the only thing I can think. This again is the Crookes, and the glass is out here, and the spinner is in there. Now, black and white, very little gas in here, almost no gas at all. And that's why it can spin so easily. In the gas, it would just stop almost very, very quickly. Now, I'm not showing this curve, but this is what the inside of the glass is going to look like. Now, we are going to send a whole bunch of photons through. And what are photons constructed of? You've seen those, they're the black and the white particles. The black particles, I think, the only thing I can think of is that more black particles are getting caught up in here than the white particles. And the white particles are coming through, and the black is getting held in here, almost making this like a charged plate. So the glass would be almost like a charged plate of the black particles. Well, we know that the black particles attract the white particles. They want these white particles. So these are coated with, they're completely, all surfaces of this are densely coated with electrons. Out here, you've got almost all of them gone that normally would be there. and they'd all be working together, everything would be fine. Well, now all of a sudden, everything in here is just saturated with electrons, and these don't have many. So when this becomes polarized into the positive, the electrons will be attracted to it. So that's why they spin in this direction. Okay, so, and that's because the heat is getting caught up, the black is getting caught up in here, causing this to be positively charged because of the heat. So it draws it back, the electrons, into this positive charge. This is the negative, and it pulls it back. Now, let's take it from the cold aspect. All right, let's try to work this out together. Heat is pushing electrons in and photons. Cold is sucking them out. So instead of them being forced into this, the ones that were in here, they're being pulled out. Well, what happens? The ones that are in here have to meet these. They have to come over to where these are being pulled out. Okay, so what does the cold pull out? Primarily, it pulls out the white. All right, cold is a remover of electrons. The more electrons you remove, the colder it gets. Electrons are the source of heat. They're the ones that glow. So we're sucking them out of here, the electrons. What's that going to do? These particles over here, they're going to be sucked over this way. So now we're turning this direction. Before we were going this direction. Now we're going in this direction. Because we've got to we got to pull this over to where we're sucking the electrons out. Before we were pushing the electrons in. And I think it's got to do with the glass. And the reason I say that the dark particles must collect more in the glass. And glass is silicates. Now, I don't know if they could do this with plastic. I don't know if plastic would work. Silicates would probably be pretty good because it's clear and it also is pretty dense. Glass is pretty hard and dense, and I think it would hold on to some of these heavy particles. The white ones, I think, would, because it's so clear, it would just more or less go through more easily. And they will suck the electrons out more easily. So that accounts for both directions of it spinning, but only for the glass. Now, I got a feeling that's what's going on here, because the gas is sparse in electrons, almost no electrons in here. But these are soaked with electrons. So that accounts for both activities. We push them against there, they're soaked with electrons, they don't want any more, they push this way. We suck the electrons out, they got a bunch of electrons, they want to go out this way, they suck them out this way, and everything spins that way. So spin this way with heat, spin that way with cold. I think we got it covered. All right, everything I've shown you, everything we talked about works flawlessly and only can work with dipole electron flood theory, and that is basically what a proton looks like. All the dark matter goes to the center, the electrons go to the outside and coat it. The further they are away, the less energy they have. Really tight ones are blue, a lot of energy, then the green, then the red. And the entire universe is only made of these two particles in all kind of configurations. That's the only two particles I can find that exist. And they make up light, and then the light congeals to make up protons. The protons make up molecules, and molecules make matter. Now, a lot of stuff, well, not a lot of stuff, but some pretty significant stuff is going to change. Going to be a change in chemistry, specifically biological chemistry, because biology uses the half-lives of all these molecules and all these atoms, which we never really considered much about. But a hydrogen has about 1,825 particles, not just one. And helium has like 7,000 something. When you get up into these big numbers, they take billions, or I don't know if that many, but they break down instantaneously using enzymes, but that's all biology. So we're going to have a lot of biological chemistry changes. And of course the periodic chart is going to have to change, to some degree. Space and time, distances, all that, things slow down coming through space. I've shown that very, very clearly. Redshift has to, we can't keep thinking that light never slows down. We know it does. So, and I don't know why they can't come to grips with that. In space, virtually everything changes, because now we understand, basically how the particles interact with each other. Now we can make some decisions about what we're seeing. And why we're seeing these swirling thises and that's and the blah. If you understand how it's a push to shove and the attraction of the white to the black and everything's a dipole, it might make more sense. So that's the dipole electron flood theory, and that it solves basically everything. It's just the way it is. It ain't bragging if it's true. It is true. So if it should be looked at, certainly for a possibility of an energy source, because I know we can separate that white from the black, and that's all you want is that white to run your car and everything else, because it wants to get back to a ground source, which is the black. So if you can separate it, that's it. You're good. And there could be some energy gain to that, which would be basically free and not polluting and all the other things. And then from there, you can make anything you want. This is not a bad thing. This is gonna, it's gonna be, we gotta look into things when they present themselves. All right, that's all I got to say. I think I showed you enough to support the fact that what I'm saying should be looked into. All right, I love you all. Thank you, bye.